Hey folks, good morning. This is going to be the worst teaching video I've ever made in my entire life. Are you ready? Okay, so today we're going to talk about something we're going to work on in lab next week. It's called an acousto-optical modulator, or AOM. Acousto-optical modulator. So basically what happens here is you have a laser, excuse me, you have a laser, right, it shines light out of the laser, and it goes through an acousto-optical modulator. Now, what happens here is that there's a little like transducer here. So you put in a radio frequency, we call it RF for radio frequency, a radio frequency electrical controller. So, you know, something like 80 megahertz for the ones that we have in our lab. But if you look at the specs at some of the companies that sell these things, there's a wide range going from very low frequencies around 1 megahertz to now gigahertz, which is pretty amazing. And this creates a pattern of sound waves that are moving in that direction with this frequency. Okay? So what we see is when we look outside of the AOM, we'll see that different orders come out of the AOM, right? And we can put this on a large screen way over at the end of the room, and we can measure effectively what those angles are. Okay, so now the thing is about the sound wave, right, is that the sound wave is moving this direction with the velocity of the sound in, this is a crystal basically, in a crystal. Right, so it's moving in a crystal up this way. So we're going to slightly change our point of view. Instead of looking at this in the frame of reference of the lab frame, we're actually going to look at it from the sound wave frame, right? So that the sound wave frame here is basically 0. So what we really see in the crystal now is the standing wave oscillation of the sound in the crystal. So this is like a grading of high and low densities inside the crystal. So what's basically going to happen is this thing is going to diffract off of these points, right? And so, because we know that light is a wave, it will diffract off of them, and we can use that to come up with a prediction for what the angle of diffraction is. Okay, well, let's dive into that. Okay, so what does diffraction look like? So we have, this is our sound wave, right? So dense, no dense, or light dense, more dense, light dense, more dense, right? The sound wave is just a compression wave in the crystal. Here comes our laser. Okay, and it comes in here at an angle of phi, and it goes out at an angle of phi, right? And then I have another wave coming in, and this one comes in at an angle of phi and goes out at an angle of phi, right? We're thinking of two parallel rays coming in, hitting off the sound wave, a compression pattern, and then going off into the into the rest of the experiment, right? So it comes in at an angle and out at an angle, basically hitting off of these different surfaces. Now, when these outgoing waves, when they overlap, right, we get constructive interference, and there we see a large signal. And when they don't overlap, we get destructive interference, and we don't basically see anything, right? And so this is happening on multiple levels at once, so you need all of the waves to kind of add up. You need this kind of perfect constructive interference to see anything at all. So, in order to do this, we have to think about the extra wavelength that this ray goes compared to that ray. All right, so if we think about it, these two distances are the same, right? Two parallel rays coming in, right? And these two rays are the same. So the extra distance it goes is this extra distance d, right? It goes a little bit of distance to get to the surface d, reflects, and goes another d, right? So for constructive interference, I know that lambda, right? Lambda of the light, right? The wavelength of the light has to be 2d, right? In order to have those waves constructively interfere. All right, so let's dive into that a little bit deeper. So we want to figure out what this distance d is. So I drew a distance d here. This is my angle phi. So this angle here is going to be a right angle, right? Because these are both parallel rays, right? And so, and that means that this angle here is 90. If that's 90 minus phi, that means that this angle over here is phi, right? And I know this distance here, which is just the wavelength of the, right? It's the distance between it's the distance of your compression wave from when you have more dense, less dense, more dense, right? So it's your wavelength. It's your wavelength of your sound wave. Remember, we're doing this problem in a frame of reference where our sound wave is static, right? So we're in that frame of reference. And so because of that, our wavelength is fixed, right? We have just the wavelength of sound. So we look at this and we can just do some trig, right? So wavelength sound is the hypotenuse, d is the opposite, so d is equal to lambda sound times the sine of phi. Okay, and now we know lambda light is equal to 2 lambda sound sine phi. All right, so lambdas are okay to work with, but we usually think of these things in terms of frequency. So if we want to convert this to frequency, lambda of light is going to be c, the speed of light, divided by the frequency of light, right? And now, for the sound wave, it's very similar, but we have to think about that the speed of sound is not going to be the speed of light in this medium, right? Because, right, it's sound and not light. So this is going to be the speed of sound in the crystal divided by the frequency of sound, right, times the sine of theta, sine of phi. Okay? All right, so then we can solve. Sine of phi is equal to CFS divided by 2 VS FL. We suspect that phi is going to be small, so phi is going to be approximately CFS over 2 VS FL. Frequency of the sound, frequency of the light, speed of light, speed of sound. All right, there's one additional weird thing about this, right? The light coming in is coming in at an angle of phi, right? And the light going out is measured at an angle of phi. So usually the way we think about AOMs is we put light in, like so, and the light that comes out is the reflected beam. So we usually want to find this angle, theta. And clearly looking at this picture, 2 phi is equal to theta, right? So if I know what phi is, it's this, then I know that theta is going to be CFS over VS FL. Cool. Now, one of the great things about this is now I have a way to do a variety of things. One thing that I can do is switch. So AOMs are really good switches. So by turning the sound waves off and on, I can turn off the diffraction pattern, and so I can use it to switch very quickly. Another thing that they're really good at is changing the deflection angle, right? So by changing my frequency of my sound wave, right, I can change what my deflection angle is pretty precisely, right? It's directly proportional. You can't really change the velocity of sound. That's set by the crystal. All right. So I'm going to go ahead and write now at the corner, theta is approximately CFS over VS FL. All right. So this is, well, we know that light is a wave, right? So it has to do wave-like things like diffraction. Well, wait a minute. Light is also a particle. So shouldn't it do particle-like things? Well, let's take a look. Let's see if there's a picture with particles that will show the same thing. And so the first things that we have to do is we have to think about what the momentum of light is in a particle form, right? So the momentum of light is given by h over lambda, where h is Planck's constant. Sometimes we like to use the expression h bar k for being the momentum. I particularly like using h bar k, right? And so we remember that h bar is equal to h over 2 pi, And now just by inspection, K is going to have to be 2 pi over lambda. So we call K the wave number. Cool. All right. So the energy of light, right, we know what that is. That's simply, so the energy of a photon is HFL. Sometimes I use the nu, right? And that's just bad habit, because that's kind of, I learned it as a nu, not as an F. But I do try to use F in class because it is confusing to use the nu, right? Is it a V? What the hell is it? All right, so sometimes we'll write this as H bar omega, right? Where this is like the angular frequency of the photon, and H bar is the H over 2 pi. Right? Now, that's cool. We can think of a quantum particle like light. Sorry, we can think of something like light as a quantum particle. But we can also think of sound as a quantum particle. And we call the light is to photon as sound is to phonon. It's a little quanta of sound, right? And so the equations look very similar, right? So the energy of a phonon, right, is going to be equal to E H bar omega phonon. H bar omega sound, so, or HF sound. Right, so there that's going to be the energy of the phonon, right? It's directly related to the frequency. All right, so the momentum's a little bit trickier. All right, so P is still H bar K, right? This is the wave number. And so this is going to be H over lambda of the sound. But if you remember, there isn't that perfect C connection between lambda and the frequency, right? Because it's a sound wave and not a light wave. So when I write down what the momentum is for the sound particle, it's going to be H, the frequency of the sound, divided by the velocity of the sound, right? And this is the velocity of the sound waves, and this is the frequency, right? Because we know that the velocity of the sound is equal to lambda sound, frequency sound. Just a standard wave arrangement. Okay, let's use this information to try to understand how we can think of this system as particles and not just waves. Okay, so we have our light coming into the AOM. Light into AOM, right? This is our crystal. And in our crystal, we have our phonons. have our photons, which are going up here, right? Because remember, our RF signal is coming into the AOM from this direction. Okay. So here's where it gets wacky. Instead of thinking these things are waves, let's now think of them as particles. And they have a sticky collision. Right? So they collide, boop, and then they move off as one. What? A sticky collision between a photon and a phonon? Are you freaking kidding me? We're doing some serious quantum mechanics here. Alright, so, I mean, this in a way is pretty good, right? Because we know that energy has to be conserved. So if this is my energy here, HF light, and my photon has an energy of H frequency sound, then I know that my total energy out has to be HFL plus FS. So I would actually expect that the frequency of the light has been shifted by the frequency that's driving the acousto-optical modulator. Let that set in there. That I'm actually getting a shift in the frequency of the light from the acousto-optical modulator. I also know that momentum has to be conserved, right? So the momentum here is going to be h bar, the frequency of light over c, right? Sorry, just h. And that's going to be going in the x direction, right? It's moving in the x direction. And then the photon's momentum is going to be hf sound divided by the velocity of the sound. Now it's moving in the y direction. So if energy has to be conserved, momentum should be conserved in a sticky collision as well, right? So this side, the x direction, this is going to come out as h fc over c fl over c I hat. No. Right? So let's just look at the angle, okay? So I know that the momentum, the total momentum is going to be when I vector add these two terms. And I can find out what that value is by looking at the, by using Pythagorean theorem, right? Okay. So, but we could use this to find out what that angle is, right? Because I know the angle that goes out, that I'm going to have a certain momentum in the x direction, which is given by hfc over c and hfl. And I'm going to have a certain momentum in the y direction, right? And I can use them to find what that angle is. So the tangent of theta is equal to hfs over vs divided by hfl over c. The h's cancel, and because I suspect that the theta is going to be a really small angle, I can use the small angle approximation for tangent, and I get that the tangent is approximately FSC over FL VS. which is the same exact answer that I got when I did Bragg diffraction. So, what is it? Is light a particle or a wave?